All right. Thank you very much, and see you on PD.
Thank you,
Enjoy your
sir.
session.
Yeah, thank you.
Hello, everyone. Good morning, and thank you for joining early. We'll be starting by 9:05, and this is to give room for other people to join in.
And just to let everyone on the call for those of us that are students, please go on your respective groups to send a reminder to your other members to kindly join as we're about to we'll be starting in the next 4 minutes. All right, please let's pause the group. All right. All right, just to recognize the Vice President of Lautech, the President of Covenant University, Rachel, and some of the executives are here for representing some chapters. Like our moderator Joy had just said, we'll be starting in the next 3 minutes. 9:05 will start. This is just to give room for others to join. President on the call, kindly reach out to your members, reminding them and telling them that the program is just about to start. All right, so please let's do well to boss the group, our respective groups. And we have on the call our Student Affairs Chairman, Mr. Stephen Obo, who had just joined. We also have on the call our our speaker, Mr. Chino Yerem Choko. Thank you so much, sir. And so please let's reach out to our group, the respective groups. Tell your members to join. We'll be starting in the next 2 minutes. 9:05 will start. So yeah, thank you.
All right. Good morning again, everyone. I hope we're having a good Saturday morning. Today we are here for our second edition or part of our lecture series. We had the first one 2 Saturdays ago, and this one is on the overview of drilling and completions operations. Today we will be learning from Mr. Choko. Please correct me if I'm pronouncing that wrongly. Who is a senior wells engineer. I hope we're excited to learn. The first part was really interesting and everybody learned. So I hope we're very excited to learn drilling operations and completions operations today. So safety is very important to us. If you're driving, we suggest, and this is a very strong suggestion, that you park your car somewhere and then you get out your notepad and your pen to take down salient points. If you're walking on the road, we suggest you find a safe place to stay during the course of this lecture, and you pay close attention to all the things that we'll be learning from Mr. Choko today. So if you are excited to learn, as I am, please drop a thumbs up in the comment section. Okay, so my name is Joy, and I am your master of events for today's meeting. Give me a minute. I'm trying to move the slides. And okay, for some reason it was stuck for a while. So this is our agenda for today. Our speaker has 40 minutes for his presentation, and the event is for an hour. So can we have Mr. Stephen Obo, our student chapter liaison, give us the welcome address, please? If he's on the call, can we have him give us our welcome address?
All right. Good morning, everybody. My name is
Good
Stephen
morning,
Obo.
Mr. Stephen.
Okay, confirm you can hear me.
Yes, please, we can hear you.
Okay, all right. My name is Stephen Obo for those who don't know me. And I am serving as the Student Affairs Chair for SP Lagos section. Also doing this role with Ovie, who has been very, very, been a wonderful guy in terms of organizing program. As we're aware, this series today is in continuation of what we started earlier this month. The objective is to try to give some background understanding of what petroleum engineering looks like especially for students who are members of our chapter, but who do not have that petroleum engineering background. So this is more or less like would I call it a webinar that will give you some great understanding of what happens in the industry. We started with hydrocarbon generation last week, and we've also pushed it a little now to drilling and completions operation. And there's also going to be production optimization sometime next week. I don't need to tell you the story about Choco, but in summary, I'll tell you Choco is a wonderful, excellent engineer who has great passion in doing this. And at the end of the meeting today, you'll be able to tell what I'm saying. Well, like I told us last week, let's keep an open mind, get your writing items, take note, and ask all the questions. Choco will be ever willing to give explanation to all the things you seek to understand. Thank you very much, and I want to pause at this time and say thank you for coming for this meeting. Over to you,
Thank you
Joy.
so much. Thank you so much, Mr. Stephen, for the wonderful welcome address. Thank you so much. We're happy to have you. So please, if you have questions, you can drop them in the chat box and they'll be attended to at the end of the lectures for the day. So, and if you also have contributions as well, please drop them in the comment section. Do your best, please, to keep yourself muted unless you are called upon to speak. And please don't draw on the screen. Thank you so much. Mr. Choco holds a first degree in mechanical engineering from the Federal University of Technology, Owerri, and a master's in petroleum engineering from Heriot-Watt University in Edinburgh, Scotland. He has about 12 years of oil and gas experience, spanning drilling, completions, and well interventions with ExxonMobil, and currently works as a senior wells engineer with Seplat Energy. I know you think this is very short, this intro is really short, but from his lecture today, you'll be able to tell that his knowledge or his well of experience runs deep. So Mr. Choco, we're happy to have you today. Kindly unmute so we can, hear you well. We can see that we can hear you, and we can also test your screen to see that we can see your screen very clearly. Thank you so much for joining us, Mr. Choco. We are so happy to have you.
Thanks for having me. Confirm you can hear me, please.
Yes, we can hear you, but your voice is a little low. If you could please increase your voice, sir, so we can hear you well.
I'm out of state, went for an event and I lost my voice. So I'll do my best to scream.
No, please don't scream. We'll do our best to hear you too. Thank you so much for taking our time for your busy schedule to speak to us and to teach us today. Thank you so much, sir.
Thank you very much for having me. And sincere apologies for moving this meeting. I know it was meant for 11 o'clock, but at that point, I'll be headed to the airport and I won't be able to give it my very best. That's why I asked that the meeting be moved earlier or later. So sincere apologies for anyone that this has obstructed your schedule for the day.
Fine,
Okay.
sir.
So just give me a minute, just a few seconds, and I will share screen in a bit. But while I'm trying to pull that up, I'm trying to have a feel of the room. I see we've got students from different schools. Is everyone here petroleum engineering student?
No, sir, I'm a geology student.
Oh, okay, great. So what other courses do we have?
I'm a mechanical engineering student, sir.
Nice, that's a family member. All right. Oh, great. Awesome. Who else?
I'm a chemical engineering student, sir.
Chemical, nice. Who else?
Metallurgical materials engineering.
Math, okay. That's awesome. Who else, please?
I'm a computer engineering student, sir.
Nice. We're heading towards the era of automation for everything, so you're welcome. Who else? Okay. From all these introductions, one thing we can pick out is every single discipline that has introduced themselves on the call are all part and parcel of the oil and gas family. Every single one, right? Be it civil engineering. Again, we do a lot of constructions, we do a lot of projects, we do a lot of cementing, right? We do a whole lot of structural design and execution. So you're part of the family. Maths, we do a lot of materials and metallurgy. Corrosion is one of the biggest issues that we have in the industry. It's actually a multi-billion-dollar industry on its own, fighting corrosion, right? So that is something that, just to let you know that that's also, you're part of the family, okay? I had chemical engineering, process, everything. If you like drill the best well, if you do not produce it, then there's really nothing going on. So process engineering, you name it, that all falls under chemical. Geology, again, I heard that you guys learned about how oil is formed, okay? Now, that's where it all starts, the geology. And if we do not have that in place, then we do not have any oil. So every single person on the call, I had mechanical engineering. Again, we run tons and tons of machines. I started off as a mechanical engineer before I got my master's in petroleum, right? So what am I saying in essence? You all are part of this family. It's a very large family. It's a family that deals with a lot of risk. And I like the fact that you started off with safety. Right? Everything we do starts off and continues with safety. Okay. Today, we're going to be looking at drilling completions, overview of drilling completions, and operations. While I was putting together some things, it struck me that what we are dealing with is not just drilling and completions, but some focus on operations. Let me share a screen and do confirm you can see my screen.
Yes.
Okay, great.
I can see your screen.
So I'm tethering with my phone just in case it cuts off. I'm not at home, so I don't have the great internet back at home. But I believe this should suffice. We've got about 40 minutes, of which I've used 3 for intros. I'll just dive right in. If you've got questions, please feel free, drop it on the chat. I won't be monitoring the chat so that I can have the full screen. But as we go through, I'll try and time myself so that I stop. 40 minutes takes us to 55. Yes. Okay. Wow, that's really pushing it close. Okay, so I'll do a little bit of well planning, do a little bit of overview, and for completions, do a little bit of drilling completions, operations, identifying rigs, the different operating environments, the types of the rigs, the systems that we've got. I will not go into the guidelines for selecting drilling rigs and importance of rig inspections. I won't go into that. But if questions come up to that, I would answer them. I put this together to try and just speak to. Okay. To try and speak to the well life cycle. Now, wells typically last from anywhere from 10 years upwards of 50 years. We have wells that are like 50 something years in Nigeria, and some of them are still producing, right? So wells last a very long time, and it starts off from the design, goes into the construction, and goes into the operations. So the green, the operation, that's where most wells stay the longest. So some of them could stay about 20 years in that space, 30 years in that space, 40 years in that space. And then somewhere in there, they keep cycling between operations and intervention, back to operations, intervention, back to operations. And when there's no further utility, it goes to abandonment. Okay. Now, what you have at the top is the same thing at the bottom, just in a cyclical pattern, showing what I was talking about, the cyclic mode between well planning and operations, and then production and maintenance operations, right? It just keeps cycling there. And then if there's no further utility, it goes into the suspension or plug and abandon bucket. So that is how it is. Now, every single person on this call, you'll find yourself somewhere within this life cycle. Some of us start from the very beginning and go all the way to the end, which is what we have in drilling. We are every single phase. Some other people, like chemical process engineers, find themselves more in the operations. Someone in civil will find himself or herself more around the construction, right? And somewhere around abandonment. So we're all, and someone in computer science, automations and control systems, you find yourself almost everywhere. Okay, well planning. Again, because of our time, I would be as fast as I can, but I will try to ensure you get the meat of what we're talking about. Now, well planning is where it all starts from. We've got lots of things. You have opportunity generation. You have things where teams that come together to ensure that we're not just putting money, we're not drilling blindly. Nobody here has gone to the subsurface, right? But we have a lot of tools that we use to infer what the subsurface looks like. And that is where you and I all come in again. And what we try to do at this phase is ensure that we are advising the client on how best to utilize and maximize the funds that are available. And there are lots of processes, right? This is different companies have different ways they go about it. But it starts with establishing a team, collecting the relevant data, choosing your casing set points, and also your sizes and configuration, determining your directional profile. Then you have other things to also consider. We're not going into all of this because this is trying to crunch 3 weeks of lectures into 40 minutes. So it's a tough call, but let's see. Now for the team, this is what the team looks like, right? You've got a geoscientist, you've got a reservoir engineer, you've got completions, and so reservoir engineer, most petroleum engineers fall into reservoir, right? Then you've got petroleum geoscientists and geoscientists, they fall under the very top. Completions and subsurface engineers, that's where you've got drilling and completions guys, that's where we fall into. Constructions and facilities, that's where you have a lot of project folks, civil engineering folks, that's where we fall into. Regulatory and public relations, again, in the industry, you'll be moved around. So you will not be in one bucket for all your life. It's only very few of us that stay in one function and build great competencies in that function for a very long time. And that's also because some functions, you do not have the luxury of training people and retraining people very often. So once you start training, you want to keep those people in that function for as long as possible. Then you've got your marketing partners, you've got procurement and KQC, and the different things that we do to ensure that we plan the well effectively. Now, our role as drilling engineers within the team is to design the well, develop the cost estimate, and manage the risk, right? Managing the risk is very, very crucial to us. I'm not sure how many people on the call have heard of Macondo, but I want to believe most people. I'm not sure how many people on the call have heard of Piper Alpha. Piper Alpha was something happened, I think, 1984 in the North Sea. Over 80 lives were lost at sea because I think one platform, Piper Alpha, went down. So the business we do is a very, very risky business. We had instances where some government officials went offshore, and by the time they came down from the chopper, they didn't even want to come down because they can't imagine how people work and live in this type of environment. A friend of mine described the offshore environment as the very first time he went there, chopper dropped him, he came down, stood on the heli deck, and he said, as far as the eyes could see, Omi, water, all around him, right? So it's serious business. So manage risk and then maximize value for the client, okay? In terms of well objectives, some of the things we do is to ensure that we understand what the client wants to do. Is this an exploratory well? Is this an appraisal well? Is it a development well? Is it an infill well? What data is available? What can we truly do, right? We are not letting the client know that it's not taking the key to a candy shop. No, it's trying to help the client, provide clarity to the client and let them understand that, yes, you've got a lot of things you can choose from. However, there are constraints that are limiting you to what you can actually do and what we can truly do, okay? So that's what we go about establishing the objectives. When we understand the objectives, then we now start going to the next phase. So a quick learning check, feel free to drop it in the chat. What are two important things to consider in well planning process? I mentioned it when I talked about the environment where we operate in, and also what you're trying to do for the client to ensure that the money they're bringing to the table. All right, so manage the risk and maximize the value for the client, right? Well-designed options should be reviewed with client organization. Is that a true or false? I said something about taking a key to the candy shop. All right, it's true, but it's not completely true, right? It's not, the client just can't pick and choose. When designing wells, there are limits that we design within, there are boundaries. So there are things that we can and cannot do. So we need to ensure that the client understands the risk and also the cost associated with their stated needs. All right. Talking about data. A couple of data is required, right? The very first one is your bottom hole pressure sheet. And that's where we work very closely with the geoscientist and petrophysicist, because without this sheet, we drill blindly. We would have blowouts, we will have well control incidents, and we're going to have kicks. A kick is influx of unwanted fluid into the well bore, okay? And when that influx is not controlled, it leads to a blowout. And when blowouts happen, most times people die, we lose lives, we pollute the environment, and those are the kind of things that we don't want to do. So the blue line, for those who do not know, so this is a chart that goes from the surface all the way to the bottom. So if you look at the axis to the left is TVD, true vertical depth, meaning as we go down in a straight line. And what you have to your right on the x-axis is the mud weight. And what we do with the mud is try to prevent the borehole or the well bore from collapsing. a lot of us have boreholes in our houses, in the estates we live in, and in our schools. Now, when you drill a hole, the earth is trying to, once you make a hole, the earth is trying to collapse against that hole. So what the mud weight does, or the mud we use, is to keep that hole from collapsing. And how do we do that? We ensure that we apply a mud that's got enough weight to keep it from collapsing. Okay? Now, we also don't want that mud to not have too much weight and end up fracturing the formation, which is the red line, right? That's your integrity line. And then you've got your overbody, which is the black. So whatever we're doing, we need to stay in between the blue and the red. So that's a very, very key stuff. And we get useful offset data from, the next thing is to collect offset data. Offset data is, a lot of times when you're going to drill in a field, you're not the one drilling there first. Someone has drilled, even if the person is not very close to you, someone has drilled. You'll find yourself in a grid, and you could find other operators having wells all around you. So we try and go collect data, either from your prior report, from stick charts. And stick chart is basically a way to compare apples to apples, okay, on a TVD basis, because a lot of times these wells are not straight. So this is TVD, true vertical depth. A lot of times the wells are not straight, never straight. And that's because you're constrained on where you're drilling from, your surface location and where you're going to, okay? Now, what that does for us is stick chart gives you a consistent way to compare apples to apples. And a good offset well is a well that drilled through the same types of formations. So at times for your top hole, so when we say top hole, when we're drilling, we do not drill all at once. There's no way you go from 0 to 10,000 feet empty or 6,000 feet TVD at a go. And that is because of this graph here. Because the moment you drill a straight line, say you're drilling with 10 ppg mud, right? I'm not sure if you can see my cursor, that's 10. You drill all the way here, you can't continue because the moment you go with 10, your formation is now higher. So it's going to push in the fluid into your well bore. And a lot of times those fluids, you do not want them at that point in time, right? So here we drill down, we increase the weight to somewhere around maybe 13, drill down, increase the weight to maybe when we get to 10,005, we increase the weight again to maybe 14 and then continue. So for those different hole sections, you need to ensure that you're looking at the right offset wells. So this is what a stick chart looks like. So I'm comparing the Lager 20 well to the Lager 53 well, and I'm checking where did they set the casings, what mud weights did they use, what issues did they have. Oh, at 10,593 feet, they had a well kick, right? They lost returns. They spotted a lost circulation material. They reestablished circulation, right? With 17.6 ppg mud. They were drilling with 17.1, meaning that at that point in time, this mud was not adequate to keep the well back, right? So we all work together to ensure that we have all that information. The next thing you're trying to do, another way to compare apples to apples, is days versus depth curve. So to the y-axis is your measured depth. Unlike the other charts where we saw the pore pressure frag gradient chart, which showed us the true vertical depth, the days versus depth is not looking at true vertical depth, it's looking at measured depth, okay? And then you got days. And what this shows you is efficiency of your drilling. And when you plot, you then realize that, okay, maybe a well is spending so much time. There's some things we call drilling on bottom time and flat time. Flat time is when you're not making any hole, meaning in terms of measured depth, you are at the same depth, but days are counting. Take this blue line, for example. This is a flat time. Okay, that's a flat time. Then you start making hole again, flat time, making hole again, flat time, making hole again, flat time. Now, flat times are okay. Those are the times when you're running your casing, you're cementing your casing. Those are okay, but you need to make them short. Reason being, time is going, and time for us is money, right? I'll tell you a quick story. When I got married back in 2014, so while I'm telling the story, let's take this learning check. What is the most important piece of information in the well planning data package? I said something. Without that, you're going to have issues. you're going to have an influx of unwanted fluid that could also, if not controlled, lead to a blowout. So you could drop that in the chart while I tell my story. And I used to carry two phones back in the days, and that's because I wanted to ensure that the rig could reach me at any point in time. Then my wife, feeling like my phone was always buzzing, and I was sleeping, so she didn't want anyone disturbing my sleep, she turned off my phone. And when I woke up, I got probably 6 missed calls. And I had to let her understand that any 1 hour the rig waits on me and they can't get me, that is $65,000 lost. And we were running 1.5, one rig line was $1.5 million per day, the other rig line was $1.65 million per day. And you know what $65,000 is like? It's like taking a Range Rover Sport, back then it used to cost about that, and throwing into the Atlantic Ocean. So you drive one brand new car into the Atlantic Ocean and it's lost forever, right? So you want to ensure that those flat times are shorter, the on-bottom times are also shorter. So, okay, we talked about it. Is the bottom hole pressure sheet, your pop pressure frag gradient, and your mod weight plots. That's what ensures that we do not run into issues. What makes a good offset well? I talked about it when I was saying the different things, different hole sections, and to ensure that a well is actually a good analog for that hole section. A well could be a good analog for a top hole, but not for your intermediate hole. And it may not be for your production or drain section. All right, close by, drilled recently, penetrated similar formulations, and a good analog design. What should be prepared quickly to communicate data gathered from offset wells? When I started comparing on bottom versus flat time, what is that curve called? Miss Joy, please, are people dropping dropping the responses in the chats?
Yes, there are
Oh,
responses in the
great.
chat.
Okay, all right, awesome. So stick charts and then your D's versus depth curve. All right, let's go to casing. Apologies if you think I'm rushing. It's just trying to give you so much data for so much value for your time. Again, like I mentioned, this is like when I worked my drill engineering school, that was 3 weeks of gruesome lectures. You're trying to compress 3 years of people's petroleum engineering study into 3 weeks of study, right? But tailoring it for the industry. We started lectures 7:30 every day, close 5 p.m. every day. The next day you have an exam, and imagine doing that for 3 weeks. So apologies if it seems I'm rushing. Now, when we make a hole, like I mentioned, the hole would always want to collapse. So you use your mud weight to keep it from collapsing. But when you do that, your mud is not going to stay in there forever. The reason why we're making a hole is to produce oil. And for us to produce oil, we need to figure out a way to ensure that we keep the hole from collapsing, and then put a pipe in there where the oil then flows in back to the surface. And what you've got here is a typical schematic that we use to represent a well. So you've got all the way from the bottom, you've got the tubing, you've got the liner, and then you've got your production casing, you've got your intermediate casing, a surface casing, a conductor, and then all the way back, right? Those are the things that keep the well from collapsing. At times, we do all of these, and areas where you have active tectonic activities, you see the earth actually move and it will share this. That's why we need materials and metallurgical brother in the room to ensure that we are choosing materials that are fit for service. All right. I won't dwell so much in this. Again, some of those casings are for structural, some of those casings are just to protect the environment, other casings are to protect the fluid. Back to these charts, right? And let me go to where a good place to talk through it. All right, good. So this is what I was saying. When the black line that goes like a stairway, that's your mud weight. So you start off with a particular mud, you stop somewhere, set a casing, and then increase the mud weight so that you can have room to drill longer. Because if I continue drilling with this mud weight, guess what? I'll stop here, because the moment I drill below this place, I'll have a kick. A kick, again, is influx of unwanted fluids. But I have to stop here, move it to the right, so I can drill for longer. Move it to the right and drill for longer. And every time I move to the right, I'm increasing mud weight. Okay? And I have to set casing so that I protect the formation before I increase mud weight. Because if I just increase mud weight like that, what happens is, imagine I'm increasing mud weight to this mud weight over here. It's above this, your integrity line, your fracture gradient, meaning I would have fractured this, and to fracture is to force the formation open. And what happens is that you're going to lose all that fluid to the formation when it's fractured. But that is not all that we require. We also need the stability mud weight. Because if I just use my pore pressure fracture gradient to choose casing set points, this casing, how many casing set points do we have here? 1, 2, and 3, right? But that's not all. I also need my stability mud weight, and that's because of these risk factors. Tectonic stresses, like I mentioned, high inclinations, your azimuthal directions. So this is what it will look like when I layer my stability. When I show my unstable shales, if I drill into this unstable shale with that mud weight, what will happen is that the shale will swell and it will break out. What I'm trying to prevent, I won't be able to prevent it. So this is what the mud weight will look like when that happens. Because I need to avoid this shale. I need to avoid that shale. Because at the end of the day, I'm setting more casings. Because what will it profit you and I to drill a hole and end up losing it? I remember one of the wells back in the days, we lost a hole, and each time you lose a hole, if you, like, for example, if you lose the BHA, that's like $4 million. Just the BHA, $4 million. If you lose the hole, you'll need to share off, plug that BHA, sidetrack. That entire work is anywhere between $10 to $15 million lost just because someone did not account for these unstable shales. Right. All right, surface casing. Apologies, I won't take this, is because of the time. Casing sizes, all right, let me go straight to the end. Yeah. Now, this is the way casing sizes are selected. We'll start off from the tubing. How much of oil do you want to produce? And that how much of oil do you want to produce is done with some production modeling softwares like Prosper. And what that does for you, it incorporates the energy of the reservoir, which is the reservoir pressure, the topside constraints, which is the back pressure in the well, the different constraints within your well bore, and then tries to model something to say, oh, this well can do 10 kbd. 10 kbd is 10,000 barrels of oil. Or this well can do 4 kbd. And it can do 4 kbd for 4 years or for 20 years, that kind of a thing. And then for us to do that and maximize, again, remember what we said, maximize value for the client. For us to maximize value, oh, we need to do a 4.5 inch tubing, or we need to do a 3.5 inch tubing, or no, we need to go up to a 7 inch tubing. Okay, so that consideration, once you align on what you're doing, you then design outwards. So we don't design, even though we drew from top to bottom, we design from bottom back to top. So what size of tubing? What casing? What hole size can you put that? What casing size can you put that tubing inside? Then that casing size, when you know that casing size, what hole size can you drill for that casing to be put inside? Take, for example, 4.5. I can put 4.5 inside a 7 inch. But if I'm going to put a downhole gauge mandrel, maybe I need to go up to a 9.58 inch casing. Now, for a 9.58 inch casing, I cannot drill a 10 inch hole for a 9.58 inch casing. I need to go up to like a 12.25 because I need to put the casing inside the hole. I need enough room to cement it. Remember, I said we need to cement it for structural integrity. And then you design outwards. The next casing size, the next casing size. And that's what you keep doing all the way to get back to your top. All right. Apologies, I won't be able to, because of our time, go through the tubing selections. But let's go to directional profile. Please feel free, drop questions. I'm trying to ensure that I go through some of the things that we have within the time remaining. It looks like I have barely 12 minutes. So this is what directional profile looks like. Why do we have directional profiles? A lot of times where you're going to and where you're starting from are not the same, and you can't do anything about it, right? Sometimes we don't even want to drill directly from above the reservoir. Maybe because there are shallow hazards, maybe because there's wildlife that we need to be protecting, maybe because there is fresh water aquifer that we need to protect. So where your facility is and where your reservoir would be located at two different places. So you need directional profile to drill all the way to that place. So for those who live in Lagos, at times your top site could be in Lagos and you're drilling all the way to Ogun State, right? So that's the way it is. And maybe because there are houses there are schools there, you can't position your rig on that location. So these are different profiles: build and hold, S-turn, horizontal well, okay? Now these are some of the other reasons. Because maybe you have a thin reservoir, you want to increase your contact, because the higher the contact, the more you produce. Or maybe it is stacked reservoir and you want to get all three. So you need to line up the well in such a way that you can get all three. Okay. Permit me to go past all of this. Let's go to completions because of our time. What is completion, or what are completions? For completions, this is a way to produce the fluid, right? Design, select, install tubing, different tools for monitoring the reservoir, monitoring the production, and getting that crude oil back to surface. If we drill a well and we do not get the oil back to surface, then we are most likely drilling an exploratory well, which is where we go trying to confirm if there is crude oil presence, right? Or we're drilling an appraisal well where we go trying to confirm how much of that crude oil is available. Or we're drilling a production. But when you're drilling a production well, it is for production. It is to produce crude. In that case, we need to have a conduit, a straw, so that the fluid can come back to surface. And that's what completions are. And completions must be safe. They must be efficient. They must be economic. And types of completions, you've got open hole completion, cased hole completion, you've got liner production, gravel park, you've got a deviation or your horizontal completion. And inside that conduit, you've got a tubing. You need a way to hang the tubing, which is called your packer, right? At times, the tubing has extension below it, which is called your tailpipe, right? Miracle David, if there's a question, kindly put it in the chat. And at times, you have multiple conduits. You're trying to get into two reservoirs. NUPRC, that's former DPR. NUPRC, the regulator, may not allow you use the same tubing for two reservoirs, especially because they want proper accounting. And what is proper accounting? They want to be sure that reservoir A, if you say reservoir A has 7 million barrels of oil, we need to be sure that we've produced that 7 million barrels of oil. Reservoir B, we need to be sure that we've produced whatever it is, okay? And at times, if the reservoirs are in two different pressure regimes, one reservoir is, say, 5,000 PSI, another reservoir is 10,000 PSI. If you produce both of them together with the same tubing flowing at the same time, you will never produce the 5,000 PSI one, because the higher pressure one will always come up first and choke back the lower pressure. It will apply a back pressure on the lower pressure reservoir. So that's why at times you then need multiple conduits. So this is what an open hole completion looks like. You just drill this in competent formations, and the thing just flows inside your casing, right? Then if you decide that you don't want to just leave it that way, you can put a slotted liner in there, which is what we have on the right-hand side. And when you start producing, the formation will collapse around that slotted liner. And at times, you've got cased hole completion. So cased hole is when we then take the casing all the way into the reservoir, cement it, and come back and perforate so that we can now reestablish communication with the reservoir. Again, this is what it would also look like. You've got liner. So liner is when we don't take the casing straight. A liner is a string of casing that does not run all the way back to surface. Now that's gravel pack is when you run the casing all the way into the reservoir, or a liner all the way into the reservoir, perforate, and then pump gravel, which is your sized sand, into that space to ensure you keep that formation from collapsing and prevent sand from being produced. Because when you produce sand, you end up killing the completions. These horizontal completions, especially when you have a thin sand or you want to increase your contact. So this can also be either open hole or it can be cased hole. All right, so this is the word I was talking about. I'm just going to use this to talk through single and multiple zones. So if it is single, you only would have, so there's what we call single selective. Single selective is you still have two sands, but only one well, and you have a sliding sleeve. So you produce the lower zone until the lower zone waters out or dies. You come in, you set a plug in the tubing string, shift open the sliding sleeve, then produce the upper zone. But if you cannot wait 10 years, 20 years to do that, you want both to come up at the same time. And you can do that for multiple reasons, right? Either there is political instability, oil price is dropping, and you want to get your oil maximum value immediately, you do this. But you also can do this only if you have enough room to put two tubings in the casing. Again, managing your client's objective. Sorry. Okay, the missus was calling me there. All right. So again, managing the client expectations, and if it's a 7-inch casing, you can't put two tubings in there. Okay, so those kind of things. So here from the bottom, you've got your tailpipe, you've got your screens, you've got a parker, you've got something that looks like a sliding sleeve. You come all the way, that is it for the lower zone. Now for the upper zone, you have the same thing, and then it just carries on all the way to the surface, okay? This same thing, but this time around, not of a deviated well, but of a horizontal well. You have packers isolating each zone, and you have flow control models in each one. So each zone contributes, and you have like a flow control device, either an inflow control valve or an inflow control device. It could be autonomous, it could be just a regular one. And why do you do this? You don't want a situation where one zone waters out and then it chokes back oil, because in this type of designs, a lot of times your heel will pull water fast, and the moment water comes in here, forget it, no oil is coming from this leg anymore. So you want to have something that can make the production even, choke back water, and you have value maximized for the client. So there are different reasons why we do all of this. Okay, 3 minutes. Let's look at rigs. So rigs and categories can be due to the environment, land, near shore, offshore, Arctic. It could also be by the derrick height. Is it single derrick, double derrick, triple derrick, quad stands? And derrick height is what helps you make up your drill pipe. So at times when you make up a drill pipe, can you make up a drill pipe in doubles, which is 2 drill pipes together as one, and run it like that? Or you make it up 3 drill pipes, which is a stand, triple, or quad stands, 4 drill pipes together. So that's your derrick height. Hook load capacity, 0.5 million pounds, 1 million pounds, 1.5 million pounds. That tells you how much you can pull. When you're drilling horizontal or extended reach wells, this matters a lot. If you're using a 1 million pound well and that pipe gets stuck, if you pull above the capacity, you damage your rig. And when that thing snaps on the rig floor, somebody can die. Because there's so much energy that was in tension released, and it slices through people. Okay, so we need to ensure we are sizing our hook load the right way. so that when you drill to TD, you can actually pull everything back out. Well depth, again, are we drilling to 5,000 feet, 10,000 feet, 20,000 feet, 40,000 feet? What are we drilling to? You also have water depth. In addition to that, well depth. Not all wells can work in all water depths. If you're using, say, a jackup rig, and you want to drill in 1,000 feet of water, 3,000 feet of water, there's absolutely no way that's going to work. So at that point, you need to get a semi-sub or you get a drill ship. By horsepower, horsepower is what your pumps can output. Now, for your circulating system, you need to pump the mud from the rig floor all the way into the well and push the cuttings out of the well all the way back to your shale shakers, which is where you separate the mud from the formation that you just drilled, back to the pit. So you need enough pressure or enough horsepower to do all this round trip. Again, is it a 1,000 horsepower pump? Is it a 2,000 horsepower pump? Is it a 3,000 horsepower pump? So all of these matter a lot. Is it a drilling? Is it a walkover rig? Is it a completions rig? Right? So those are different things that you put into consideration. And this list is not exhaustive, right? Is it by land? Is it amphibious? Are we in a land location? Are we in a place where we have snow for half of the year? Is it an offshore environment? If it's offshore, what water depth are we at? Right? Is it in a very harsh environment where we're going to be having hurricanes? So those are things to consider. So I'm just going to, within the next 2 minutes, run through this. This is what a typical land rig looks like. So when you go to places like Egbema, in Imo State, places in River State, Delta State, you see a lot of land rigs. So they clear the area and put this in place. You put a pad and it has to be such that the foundation can carry it. Right? A barge rig, the swamps of River State and Delta State and Bayelsa State, this is where you see this type of things, right? A swamp rig. Again, this goes from less complex to more complex, less expensive to more expensive. Okay. Now, when you have marshy water, this is the kind of rig that you use. When you see something for all of them, you see something that looks like an MTN mast, right? That's what you call the derrick. Okay, platform rigs. Platform rigs, this is where you have a rig that is drilling and combined with production. So we have them in so many locations, and it's usually offshore. So this rig doesn't move, it just stays permanently. And it has its own limitations also, because once the slots are filled, you then end up having to plug and abandon, reclaim the slot for you to drill new wells. So you are limited. This is, oh, I missed one. Apologies, a jackup rig. A jackup rig is different from this. What it does, it has legs. The legs must penetrate the formation. It's usually used for offshore, but the legs must, so it looks like this platform rig, but the legs must get into the mud line for stability. Then you jack up above the water and you then start drilling. Semi-sub, you typically use semi-subs for offshore environments. The leg doesn't get to the bottom. It's a floater. So depending on these four corners, depending on how much water you put in there, that will give you the draft, how low it goes or how high it comes up. Then the last one is a drill ship. There's one more after this one, but this is typically what we use, drill ships, and use them for deep water operations. This one floats, right? And you have heave compensators to help you maintain stability. Some of them are DP, which is dynamically positioned, or you use mooring chains to hold it in place. And when there's harsh weather, it rotates to align itself with the weather without obstructing what you're doing. So the picture to the top, you see it has one derrick. The picture to the bottom that's only showing the derrick has two derricks, right? So that's used for dual activity. Those are some of the things that it works well. Then you've got your Arctic drilling. These are usually in areas where you have maybe only 3 months of free time to drill. The rest of the 9 months or 6 months or 8 months, everywhere is frozen. Okay. Rig systems, I'm not going to go into this because of our time. So time is really gone. But we've got power, hoisting, rotating, circulating, and well control. Power is your generators. What's the total power requirement for your hoisting system, for your mud pumps, for your well control package, for everything you need? How much power do you need? You size it properly. Hoisting system is what you use in lifting and lowering, right? Your drill pipes and your tubing, so whatever it is you're running the well. Your rotating system is what you use to rotate, because you need to rotate for you to drill. Okay, and that could be, back in the days they used to use a Kelly bushing, but now we use top drives. And you've got your circulating system, like I talked about when we were looking at the mud pumps earlier. That's what it starts from. The mud pumps goes from your stand pipes all the way through the drill pipe down to the well. You push up the cuttings all the way back to your shell shakers and then back to the mud pits. Then your well control package is to ensure that you do not have a well control incident or a blowout. So I'm going to pause here. I've overshot by 4 minutes, so sincere apologies. And if you felt I was quite fast, again, sincere apologies. The time was quite short. I hope I've been able to deliver. Thank you.
Thank you so much, sir. Amazing session, amazing presentation, amazing lecture. Thank you so much, Mr. Choco. Thank you so much. Also, am I pronouncing your name correctly?
Yeah, Choco, that's right now.
Oh, Choco, okay.
Yes.
Okay, thank you so much. We are very thankful and grateful that but we know you are very busy. So thank you so much for taking out time from your busy schedule to teach us today about the overview of, sorry, give me a minute. Okay. So if you enjoyed the session, can I see your thumbs up, your applause in the comment section? Can you hear me? Okay. Wonderful, wonderful session, sir. So we have some questions for you from the participants. Okay, so the first one is using linear instead of casing to subsurface, mainly for cost efficiency?
Okay.
That was when you talked about the types of wells.
No. It's not only cost efficiency. Cost efficiency is one of it. But another thing could also be the formation. It could also be the well design, right? So the well design can drive that. So it's not only cost. So cost is secondary. The first thing is managing the risk, right? So if we can manage the risk with a liner, and why do we use a liner? At times, the weight of carrying the entire casing, if you've got a casing that goes all the way back to surface, that casing could be 1,000,000 metric tons. And your top drive cannot carry that weight. If it cannot carry that weight, then you need to drop down to a liner. So it could be the well risk management that's the issue. So cost is secondary.
Okay, thank you so much, sir. Another one is from Sochima Duru. Sochima, can you please unmute and ask your question? It's quite long, so he gets it directly from you.
Okay, I understand what he's asking. I can go ahead and talk to it.
Okay.
So he's asking, what are the factors to be taken into account, especially for the drilling phase that can be later implemented in the development phase? Again, so for data, we don't go cheap on data because data helps us ensure we keep everyone safe. Our business is a business of risk management. We keep everyone safe. If we don't do that, we're going to damage the environment, we're going to lose lives, we're going to lose money, and the reputation of the company will be damaged, right? So every stage we collect data and we feed data back. If you remember the well life cycle I mentioned, how everything keeps feeding back. And what we do is, at the appraisal stage, while we are collecting data to appraise the subsurface and know how much oil is there, we're also collecting data about the formation. We are taking pressures, we are taking formation sampling, we are taking core data. And all of this will then feed back into the production phase to say, now we are going to be drilling. We look back at all the wells that has been drilled, all the learnings. That's why we do a stick chart. A stick chart will say, okay, they did this appraisal well. They had losses at this depth. The other well did not have losses. Why is maybe there's an issue here, there's a stability issue here. All of that comes into the development phase. And when you're now drilling further wells, you incorporate learnings from the prior ones. We do that at every stage. Learnings are incorporated to ensure that we keep everyone safe.
Thank you so much, Mr. Choko. So the next person is asking if the recording will be made available, and yes, it will. So can we have your slides as well? Will that be made available for participants?
Yes, that can be made available.
Okay, thank you so much. There's one question that says, do subsea wells always have a combination of structural and conductor casing? And what's the difference between them?
Yes, every well.
I think you answered that already.
Yes, I answered. Every well has that combination. The difference between a subsea well and a surface well is that rather than the casing starting on surface, the casing strings all start subsea. So when you have a surface well or a land well or an offshore well, what that does is you've got your tree is on surface or on the land. You can see it, you can touch it. But in a subsea well, your tree is at the mud line, is on the seabed. If your water depth is 1,000 feet or 1,000 meters, rather, is down there. If it's 3,000 meters, it's down there, right? And that is where your casing starts from. That's the difference. And you know, as you go down in water depth, your pressure increases. So you need to ensure that all of those things are designed very robust enough to manage that crushing pressures. If you remember the thing that happened, I think just roughly 2 years ago, with the sub that imploded, the exploratory, what do they call them? Yeah, I can't remember what they call those tiny subs that they built with fiber optics. Carbon fiber rather, reinforced carbon fiber rather than the typical way we build military subs. And the thing imploded, and all 6 lives were lost. That's how much pressure we have to deal with. So all those equipment have to be sized properly. So to answer the question, yes, every well has that, and the difference is just that it starts from the subsea. Thank you.
Submarine.
Structural casing, conductor casing. Oh, good. They can be the same and they can be different. Yeah, structural casing can be the same as conductor casing, and it can be different. You could have a conductor casing, but you still run a structural casing after the conductor pipe to keep back, protect the freshwater formation. Yeah. So they can be the same and they can be different. It all depends on how many casing strings you are running and how the company names them and the function that they are providing in that particular wellbore.
Okay, so thank you so much, sir, Mr. Choko. So Tawahid has 2 questions and he'd like to ask them verbally. So
all right, please go ahead.
We'll take his questions last. So Tawahid, please go ahead and ask your questions.
Okay, thank you very much, sir, for the wonderful section, sir. The first question is, considering a shallow offshore well where you're using a jack-up rig, why do they normally say that whenever we might have pied a conductor pipe either 24 inches so at about a point of refusal, why do they normally say that after that we nipple up our diverter and not nippling up our BOP? That's the first question, sir. And the second question, sir, considering a swamp system, a rig that, I mean, a well that has been drilled for like 40 years ago that has integrity issue, and we got to know that that particular thing, they do not use Christmas tree, they use the suspension cap, and gas is coming up in the surface. What could have been the problem? Could it have been that the packer has integrity issue, or the anger body seal is faulty, sir, or the casing is faulty, sir? Thank you, sir.
All right, thanks, Tawhid. Very great questions. You will make a great petroleum engineer. So to the first question, why did they say we are nippling up diverter and not BOP? Because immediately you finish driving your conductor pipe to refusal, the next hole you are drilling is a surface hole. And in surface hole, the formation integrity is small, is limited. If a BOP, what we use a BOP is to close in on a kick. And when you close in on a kick, that formation must have integrity to contain it. So that if you remember that pore pressure frag gradient plot, the frag gradient must have sufficient integrity to contain the kick. If it does not have integrity to contain the kick, what will happen it will broach, which is instead of staying inside the well bore, instead of staying inside your casing and being contained by the BOP until we figure out a way to bring back restore well control, it bypasses the casing, goes through the formation because the formation is the path of least resistance and comes to surface. So the rig could be here and we then have a blowout, surface blowout, sometimes somewhere further down. And if it's a land rig, guess what? It could be at a school. It could be at a residential neighborhood where that happens, okay? If it is offshore, it could be another location where there's a facility, or another rig, and everything there goes inside the water. It could even be around us. It just comes, and whenever hydrocarbon or gas comes, it lightens the water. The surface tension of the water changes. If it's a drill ship that is there, that drill ship is sinking. Now, we can do all of that with a BOP if there is sufficient formation integrity. But if there's no sufficient formation integrity, we don't want to contain it. We want to divert that influx. So that's why we nipple up a diverter for surface hole, because we do not have sufficient formation integrity to contain it downhole. So that kick, once the kick comes in, we divert it, meaning we actually allow it to come to surface and we face the diverter downstream of the wind, so that as the wind is blowing it away from us, so that the inlet of the generators does not take in that gas. And if the inlet of the generator takes in that gas, it's going to explode. So because instead of having oxygen coming, you're not having a hydrocarbon coming and everyone is going to die. So that's why we do that. I hope I answered the first question. Then second question, if that well definitely was suspended, for us to have a suspension cap and not a Christmas tree, and if the suspension plug has moved, what it means is that it was not suspended correctly. It means that the forces under the plug and the forces above the plug are not balanced. And the plug is not properly anchored to withstand the forces below it. So if it's not properly anchored to withstand the forces below it, the forces below it, net balance of forces, right? It's going to push that plug up. So what that means is that, one, it was not abandoned properly. Two, they probably did not have a proper understanding of the pressures they were dealing with, and that's why that happened. Or they did not have sufficient plug in place to contain and keep the well pressures down in the well. So for such, we need to re-enter and properly abandon the well, because NEPRC, the regulator, will not allow us leave such a well in that condition, or allow any operator leave such a well in that. So whoever has that well, they need to ensure that they reassess and go to and abandon the well properly. Because if we don't, we are leaving the environment in jeopardy. All right. Thank you, everyone. Thanks for having me.
Thank you so much, sir, for the amazing responses to the questions. I'm sure everyone that attended is pleased that it did. The session was packed, very, very packed. In a short time, there was just a lot of information. And I'm glad that the meeting was recorded and people can go over these things again and again and again to keep learning. So thank you so much for your time, sir. We are very grateful that you could make it to us today to teach us. Thank you so much, sir.
You're welcome.
Yeah. Okay, so let's have our photo session if you can, and I hope that you can. Please, let's see your beautiful and your handsome faces so we can, take a picture, take a group picture.
All right, Joe,
Please.
I think if you can stop sharing, okay, it's coming on.
Okay. So should I still stop sharing or we're good to go?
No, I just want to ensure that okay, just give me a few seconds. Yeah, just stop sharing a bit. Let me confirm. Okay. Yeah, gallery. All right, on now. All right, let's have everyone turn on their camera. We can see Kayode Adewale, Adetayo, Blessing
Blessing looks
Ben.
shy. Blessing Ben, why are you
Yeah, Blessing
shy?
is shy.
Why are you shy?
Yeah, Chaid is here, Akinloye. Yeah, we have Salahuddin. We have Marvelous. Yes, brilliant. Yeah, it's yes, we see the engineer Tawhid that asked the one of the most brilliant questions. Okay, so please let's keep it coming. Let's keep it coming. Okay, can we have more faces? I think some of us are will I say okay, just give me a sec. So we were almost done with this section. Okay. Okay. I just have Samia Bayodi, yeah, thank you. Irene, yeah, thank you. Pelumi, okay, yeah, so yeah, the OOU president, I see you. Because okay, so and we are done. Thanks a lot, Joy. Over to you. You can share your screen now.
Okay. Okay. Thank you so much, Ovi. So you're actually next. Please give us the closing address.
All right, thank you. Thank you so much. I would first of all, when Mr. Steven said that we will understand the person of Mr. Chuku, I would have said, I mean, I was so curious, like I won't let me, I mean, but I haven't seen how that he has delivered. I mean, the presentation was insightful. I never wanted him to stop. I think I'm not sure I was the only one, but I never wanted him to stop. This is to say a very big thank you to you, sir, for your time. And I mean, you're someone that outside of now, I'm not. I mean, I'm very certain of this. A lot of engineers, I mean, students here, if they happen to have your number, they will keep asking you questions back to back because the presentation was extremely insightful. And many thanks also to our student affairs chairman in the person of Mr. Stephen Obo for organizing this and also for getting to introduce you to us, because it's an honor getting to know you, getting to hear from you. It's a very, very big honor. I mean, great privilege, sir. So thank you so much, sir. And I don't want to forget this. Let's give it up for our MC. Our moderator, the person of Joy Alumuna. She's exceptional. She delivered excellent last Saturday at the beginning of the Petroleum Engineering Lecture Series. She also did, I mean, you could see excellence in anchoring not just physical events but virtual programs as well. Thank you so much, Joy. And also I want to say a big thank you to all of the students, the young professionals we have on the call. Thank you so much. The student affairs and volunteers, thank you so much. Thank you so much to all the student chapter presidents for your contribution in getting your student members to benefit from this knowledge. And I can't thank you I can't thank you all enough. And greetings from our SP Lagos Section Chairman, Mr. Dipo Achafa. Thank you so much. And we look forward to part 3 of the petroleum of this series, petroleum engineering lecture series. And also, please, lastly, let's not forget that the recording of the last one, we have it, and I think it was shared. If you don't have it, remind me to share it. And also, this program was also recorded, and we'll do it to share with you. And I also believe that Mr. Shoko is also going to share the slide pack of this excellent, wonderful, insightful, presentation. Thank you so much, sir. We can't thank you enough. Thank you, and thanks everyone. Yeah.
All right. Thank you, Mr. Uve. Thank you, everyone. It's lovely to be here. It's an honor to be here too. So please, you can now drop off. Thank you so much for attending. For those that came early, thank you too. Bye. Bye, everyone.
Please don't forget, you can post on LinkedIn, post this event on LinkedIn, tag Mr. Choco, and yeah, please do. Thank you, everyone. Yeah, bye. Have a great weekend.
Thank you, Uve. Bye, Uve.
Yeah, bye, Joy. Thanks a lot.
Yeah.